If you took a single tablespoon of a neutron star and somehow transported it to Earth, it would weigh approximately 6 billion tons. That is roughly the combined weight of every human being currently alive on this planet, in one spoonful. Neutron stars are the densest observable objects in the known universe, and what lurks inside them is one of the greatest unsolved mysteries in all of physics. Today, we are going to crack one open and look inside, layer by layer. And what we find gets stranger with every step deeper. A neutron star forms when a massive star, at least 8 times heavier than our Sun, exhausts its nuclear fuel and dies. The outer layers of the star explode outward in a supernova, one of the most violent and luminous events in the entire cosmos, briefly outshining entire galaxies. But the core, the innermost heart of the star, does not explode. It implodes. It collapses inward under its own gravity with such unimaginable force that protons and electrons are literally crushed together, merging into neutrons. What remains is a ball of neutrons roughly 12 miles across, about the length of Manhattan, but containing 1 to 2 times the entire mass of our Sun. Take a moment to process that. The mass of a star, compressed into something the size of a city. The gravity on the surface of a neutron star is approximately 2 billion times stronger than gravity on Earth. If you somehow stood on the surface, assuming you survived the journey, which you absolutely would not, you would be instantly flattened into a layer of atoms a few micrometers thick. Your entire body, every bone, every organ, every molecule, compressed into a biological pancake thinner than a sheet of paper, spread across the surface like butter on toast. But the real mystery is not on the surface. It is deep inside, where conditions become so extreme that our physics literally breaks down. The outer crust of a neutron star is made of iron nuclei arranged in a crystalline lattice structure. This material is the strongest known substance in the universe, billions of times stronger than steel, billions of times stronger than diamond. Nothing we have ever encountered or manufactured comes close. When this crust cracks or shifts even slightly, it produces starquakes, seismic events so powerful that they release more energy in a tenth of a second than our Sun puts out in 100,000 years. A tiny crack in the surface of a city-sized object releases more energy than a star does in a millennium. The numbers are simply absurd. Beneath the crust, you enter the outer core, a vast ocean of neutron-rich fluid exhibiting a property that seems impossible at these temperatures. It is a superfluid, a quantum state of matter where particles flow with absolutely zero friction, zero viscosity. Nothing slows it down, nothing stops it. In laboratories on Earth, we can only create superfluids at temperatures near absolute zero, the coldest possible temperature. Inside a neutron star, this same quantum state exists at temperatures of hundreds of billions of degrees. The hottest superfluid in the universe, flowing through the core of a dead star. Some of this fluid also acts as a superconductor, carrying electrical current with zero resistance, generating magnetic fields trillions of times stronger than Earth's. These magnetic fields are so intense that they would erase every credit card, corrupt every hard drive, and disrupt the chemistry of your body at a distance of thousands of miles. And then we reach the inner core. And this is where physics throws up its hands and honestly admits it does not know what happens next. The pressures at the center of a neutron star are so extreme, many times greater than those found inside an atomic nucleus, that neutrons themselves may break apart into their constituent quarks. Free quarks, liberated from the neutrons that normally contain them, have never been observed in isolation anywhere in nature. They are always locked inside larger particles. But inside a neutron star's core, the rules we know might simply stop applying. Some physicists believe the inner core contains a soup of free quarks and gluons, a state of matter called quark-gluon plasma that existed in the first microseconds after the Big Bang, but has not existed freely anywhere in the universe since. Others think something even stranger happens. Quarks might rearrange themselves into exotic configurations called strange matter, containing a type of quark called the strange quark that does not normally exist in stable form. And here is the hypothesis that keeps some physicists awake at night. If strange matter turns out to be more stable than ordinary matter, then contact with even a single droplet of it could theoretically convert normal matter into strange matter in a chain reaction. A single microscopic piece of strange matter touching Earth could convert the entire planet, atom by atom, into a sphere of strange matter. That is probably not going to happen. Probably. The truth is, The interior of a neutron star represents one of the very last great frontiers of fundamental physics. We can observe neutron stars from afar using X-ray telescopes, radio arrays, and gravitational wave detectors. But we cannot recreate those internal conditions in any laboratory on Earth. Not even close. These tiny, city-sized stellar corpses are cosmic laboratories operating at the absolute extremes of what matter can do and what physics can explain. And they might contain forms of matter that exist nowhere else in the entire observable universe. If you want to keep exploring the most extreme objects in the cosmos, hit that subscribe button. We have got a lot